interstellar communication would most likely be transmitted through electromagnetic radiation. They believe that the optimal frequency for interstellar communication would be at 1420 megahertz, or the frequency that the most abundant element in the universe, neutral hydrogen, emits. And they reason this would be used by extraterrestrial life due to it being a foundational frequency. And they published a paper over this in the journal Nature titled Searching for Interstellar Communications. Inspired by them, Frank Drake used his radio telescope to look for signs of extraterrestrial life. And in 1961, he created the Drake equation, which predicts the number of civilizations humans could communicate with based on variables such as the average rate of star formation, the fraction of stars with planets, etc. However, even now, almost 60 years later, current estimates of almost all of these variables have huge uncertainties, and many of these variables are probably unlikely to ever be known, such as the average length of time civilizations can survive and communicate, or the fraction of planets that can develop an ecosystem, which has resulted in some scientists estimating that the number of civilizations that humans could communicate with as way greater than one, and others predicting that it would be way less than one. Even still, although Cocconi and Morrison searching for interstellar communications and the Drake equation might seem pretty preliminary and rudimentary now, they were some of the fundamental building blocks in the field of astrobiology and part of the beginning of the search for extraterrestrial life. So from this, Project Cyclops was created at NASA to attempt to use radio telescopes to look for extraterrestrial life. However, since they asked for a budget of $6 to $10 billion to build and use a radio telescope array, the project was canceled. A little over 10 years later, in 1984, the Search for Extraterrestrial Intelligence Institute, or study, was officially created. And although many side projects had been going on for a while, in 1992, they created another program called the High Resolution Microwave Survey Targeted Search, but Congress also deemed it a waste of taxpayers' money and terminated it the next year. Thus, they renamed it to Project Phoenix and ran on private donations to scan the sky for extraterrestrial signals. I believe now studies funded mostly by private contributions, but also from NASA and the National Science Foundation to use radio telescopes such as the Allen Telescope Array and Keck telescopes to explore the origin and nature of life in our universe. So during the time of Project Cyclops, humans were starting to send probes to the further reaches of our solar system, and along with them, universal messages in case they were someday intercepted by other life forms. So Pioneer 10 and 11, which were launched in 1972 and 1973, were some of the first spacecrafts to study Jupiter and Saturn, and brought with them a plaque with engravings of a man and a woman, the location of the sun in relation to nearby pulsars, the planets in our solar system, including Pluto, which was then classified as a planet, and other defining details about humans in our solar system. A couple years later, in 1974, the Arecibo radio telescope transmitted a pictorial message to the globular star cluster, I believe M13, which contains hundreds of thousands of stars. And as you can see in the message, over here, as you can see in the message, it included a little human, the Arecibo radio telescope, let's see, the solar system, formulas for the nucleotides of DNA, and more. And then finally later in 1977, Voyager 1 and 2 were launched to continue studying the outer planets, each of them containing engravings similar to the Pioneer plaques on a record, which contained music, sounds of nature, and greetings in multiple languages, as well as 115 encoded images of mathematics, science, our solar system, human life, and nature. So soon, a new field of study was born from the 1995 discovery of the first exoplanet found orbiting a main sequence star, which was 51 Pegasi b. In 2009, as a result of this, the Kepler Space Telescope was launched with the sole purpose of looking for exoplanets, and after finding over 2,000 new exoplanets, was retired in 2018, which is also when the Transiting Exoplanet Survey Satellite, or TESS, was launched to replace Kepler and to scan the entire sky to search dimmer stars for exoplanets. And this is also when the idea of the circumstellar habitable zone, also known as the Goldilocks zone, gained traction. So this is defined as a region around a star where it's not too cold or not too hot, and liquid water could exist on the surface. So that is a brief and definitely incomplete history of humanity's search for extraterrestrial life. And I would definitely encourage you, as I'm sure you have, to look more into this subject because there's a lot of really cool history that I didn't cover. All right, so now going into the galactic habitable zone. So when we ask the fundamental question, are we alone in the universe, and think about the potential for life, a star system's habitability depends both on its internal structure, which sets up the building blocks for life, and its external structure, or external environment, which allows life to evolve and flourish. While most habitability research is focused on these internal factors, such as planetary orbits, like with the Goldilocks zone, and the size and mass of exoplanets, there's still much work to be done to understand the external galactic hazards that could jeopardize life, which is where the idea of a GHZ comes into play. So the Galactic Habitable Zone, or GHZ, is a fairly new concept that predicts the regions of the Milky Way that would be most suitable for life, but it's also pretty widely disputed, with some scientists believing it to be a small annulus around the radius at which the sun is located, and others believing that there are too many unknown parameters to even accurately characterize the GHZ. The idea of a GHZ was first proposed by Dr. Gonzalez, who's a professor at the University of Washington, in 2001, and he believed that stars in the halo, the bulge, and the spiral arms would not be suitable for life because many of the galactic hazards present in those regions, such as supernovae, high energy radiation, gravitational perturbations, etc. And he even kind of pessimistically predicted that over 95% of the stars in our galaxy would not be able to support life because their orbits would cross a spiral arm or the center, which he believed would wipe out any life trying to evolve in the system. So here's a table of the main models of the GHZ. And as you can see from the table, there's no generally agreed upon model. And many of the models are based on general trends and simulations. If you look though, over time, the average trend for the predictions for the GHZ are becoming wider. With the most recent one, the simulation done by Forgan et al. In 2017, predicting that stars with a radius from 2 all the way to 13 kiloparsecs from the galactic center, that they would be able to hold life. So now going a little bit into my work on the GHZ. So what really sparked this project was Gaia, which was a satellite launched in 2013 by the European Space Agency with a goal of making the largest, most precise three-dimensional map of our galaxy by surveying over 1 billion stars. And so because there's so many stars in this database, which is free online, so you can totally like download data and just play around with it, it allowed me to use stellar data rather than simulations or general trends to more accurately model the GHZ. And so this project, the goal of it was to develop a model for the GHZ and apply it to stellar data from the Gaia satellite on over 6 million stars, including almost 1,500 exoplanet systems from the NASA confirmed exoplanet archive. So this model consists of the following criteria, which encapsulate many of the commonly accepted factors that affect habitability. So first is avoiding the bulge, where harmful radiation and gravitational perturbations are incessant due to the supermassive black hole and large density of stars located there. Next is avoiding the spiral arms, where there are more frequent supernovae and other hazards due to increased rates of star formation and stellar density. I actually recently read a paper about how the sun's spiral arm crossings in its orbit around the Milky Way are correlated with the timing of many of Earth's mass extinctions, which is kind of cool. And the final criteria is sufficient stellar metallicity, which is imperative for the formation of terrestrial planets that could potentially hold water. So the first two criteria of my model, avoiding the bulge and the Milky Way spiral arms, were evaluated by calculating the orbits of each star and comparing it to the locations of the bulge and spiral arms. So first, using the stellar rotation curve data from the Gaia satellite, the Milky Way's gravitational potential was estimated based upon the least square regression curve fit of the sum of 3 parts, as you see over here, the bulge, the disk, and the dark matter halo. Then, and the locations of the bulge and spiral arms were defined using previous research. As you can see, here are all the spiral arms, the 4 of them, and then the center bulge would be right here. And then finally, using the Milky Way's calculated gravitational potential and each star's current position and velocity, each star's three-dimensional orbit was calculated backwards in time over the last 4 billion years, which I chose because that's how long life has been on Earth. So from this orbit, the number of time intervals that each star spent in the bulge and the number of spiral arm intersections each star had was counted. Since the spiral arms rotate at a different rate than the stars, the orbits of each stars had to be transformed to the rotating reference frame of the spiral arms to calculate the number of spiral arm intersections. And then the metallicity was just taken from the Gaia database. So here's an example of the sun. So first we have the 3D orbit, then the flattened 2D orbit, and finally the orbits transformed to the rotating reference frame of the spiral arms. So this would be like if you were looking at the Milky Way from above and rotating at the same rate as the spiral arms and watching how the sun moved. And my calculations show that the sun has never entered the bulge and has intersected the spiral arms 33 times. So basing my criteria off of this, I defined a potentially habitable star as one with no bulge intersections, no more spiral arm intersections than the sun, so less than or equal to 33, and a metallicity at least half of the sun's, which is a commonly used threshold for a star's ability to form terrestrial planets. And here are some other examples of the 3D orbits right here, or 3D orbits right here, and the transformed orbits, and I think they look pretty cool. It kind of reminds me of those spirographs I used to play with when I was a kid. All right, so moving into results, this depicts the percentage of stars that satisfy these criteria versus their current radius. So the red is the percentage of stars that never enter the bulge. The blue is the percentage of stars at each radius that have less than or equal to 33 spiral arm intersections. The orange is the percentage of stars that have a metallicity at least half of the sun's, and the purple is the percent that satisfy all three criteria. So as seen from this graph, there seems to be stars with habitable conditions in most regions of our galaxy, and our sun's location at 8.34 kiloparsecs isn't even the region with the highest percentage of potentially habitable stars. Additionally, for the exoplanets, this is a graph of the metallicity of each star versus their number of spiral arm intersections, with the stars that satisfy both the metallicity and spiral arm criteria in the upper left. And I found that 29% of the star systems satisfy all three criteria, including 1 out of the 3 systems with Earth-like exoplanets and 3 out of 11 of the systems with super-Earth exoplanets. So going into some discussion and implications of my work, just overall, I used the largest stellar data set to date to implement kinematic and metallicity restrictions. And this work indicates that there is a potential for a habitable world in a large region of our galaxy. In comparison to previous work, these results are inconsistent with models that predict the GHZ as a small ring, which are mostly the ones that rely on general trends, and is more consistent with wider predictions, such as the N-body simulation done by Forgan in 2017. However, this work goes a step further and calculates orbits based on actual stellar data rather than simulated galaxies, which is what Forgan did. As for limitations, in the field of exoplanet research, the main limiting factor in defining a potentially habitable world is sample size of known habitable worlds being equal to 1 or solar system. So just as this work uses the sun's number of spiral arm intersections as a threshold for habitability, the accepted stellar metallicity cutoff for the formation of terrestrial planets is based or is defined relative to the sun. And of course, Earth-like and super-Earth-like or super-Earth exoplanets are defined in relation to the Earth's radius and mass. Besides the broad limitations of this field, there are several other limitations more specific to this model. First, our knowledge of the Milky Way is, or the Milky Way's geometry is incomplete, particularly the size of the bulge, the length of the bar before the spiral arms start, and the length of the spiral arms. And furthermore, these analyses do not take into account perturbations due to individual stars. So some of the orbits of the stars might be slightly off or inaccurate. And addressing these limitations would require incorporating a time-dependent potential, so one that changes every time or every step backwards in time that is taken, and defining galactic hazards on a continuum. So for example, modeling the spiral arms of the density rather than as a strict line, which is something I'm working on now. I think it's also important to acknowledge that there are a lot of potential flaws with just GHZ models in general. For example, maybe spiral arm intersections aren't such a bad thing after all. For all we know, life could have been brought to Earth from an asteroid or another extrasolar object. So it might actually be good to enter the spiral arms and get bombarded with asteroids to bring life to other planets. Furthermore, if no asteroids had hit the Earth, humans might not even be here, and dinosaurs might still roam the Earth. So it might actually be necessary to have perturbations from asteroids to continue the evolution process and to create intelligent life. And finally, many scientists actually believe that it'd be very difficult to destroy life once it has started, given that life on Earth has been through several mass extinctions, and given the copious amount of like extremophiles on Earth that live in crazy places. So there's definitely a lot of unknown factors in looking at habitability, but that's also kind of what makes it interesting to think about. So in terms of conclusions, this work contributes to the overall search for life in the universe. Many millions of dollars have been spent on satellites and telescopes, including Kepler and TESS, which are dedicated to searching for exoplanets. And by incorporating galactic habitability, this work helps to better understand, better understand the potential for life on exoplanets, systems we have found, and refine our search for life in the universe. So for example, for stars suspected of having exoplanets, preliminary analyses such as these could be performed to prioritize stars with favorable orbits to more efficiently use telescope time. On a more profound level though, the big takeaway is that from this work is that it indicates that there is a potential for habitable worlds in a large region of our galaxy. So unlike previous models based on simulations and general trends, these results provide additional evidence that there is a potential for a habitable worlds nearly everywhere in our galaxy, and that our region at about 8 kiloparsecs may not even be the most hospitable for life. However, this work also predicts that many of the exoplanets we have found may not be able to support life, as only a third of them have favorable orbits. But in any case, this work demonstrates that accounting for stellar kinematics is an essential piece in our search for life in the universe. So I can take any questions if you would like.
I have a question.
Mm-hmm.
Super interesting subject. My questions, I have 3 of them, all have to do with the spiral arms.
Mm-hmm.
So how many spiral arms does the Milky Way have?
So in mine, I used 4, but I know it's a little bit, not up for debate, but it's still being looked at. But okay. Yeah, I used 4.
Okay, and is the sun in a spiral arm right now?
Do what? Sorry.
Is the sun in a spiral arm right now?
No. So the sun would be right about over here, or if you can see my mouse, like between the 2 spiral arms right there.
Okay, and do you think it would be useful to take into account the effect of globular clusters plunging through the plane of the Milky Way periodically?
Definitely, ideally it would, but I guess this is more of a rough estimate, right? We don't, even still from this, like there's definitely imperfections in, the exact size of the bulge, exactly where the spiral arms are, but it's more of a rough estimate that for where habitability could be. So ideally, yes, I would like to take that into account, but I'm not sure if it would necessarily be possible.
Thank you.
Mm-hmm.
So this would imply that some galaxies could be completely barren if it's a dwarf galaxy that doesn't have enough metallicity, or if it's a giant elliptical that's basically all bulge. It's possible that there may be no life in a galaxy. Yeah, and there's actually like beyond the GHC, there's definitely theories about the habitability of different types of galaxies. So for example, I believe that at spiral arm galaxies, they the rate at which they produce new stars stays approximately constant over their life, but things like elliptical galaxies, they have a big
crash of star formation in the beginning, and then they kind of die out. So that could definitely impact how habitable different types of galaxies are.
Thank you.
Did she get muted? Camille, it looks like we may have lost you. Did you go on mute? No.
No, but her connection kind of fizzled.
It looks like we may have had a connection problem with Camille here. Let's see if we can get her back. I don't know what that icon is.
Sorry, I'm not sure what happened.
Okay, you're back now. So you got a thank you on the last question. I don't know if you were able to get everything in that you meant to say about that question, though.
Oh, yeah, about habitability of different galaxies. Yeah, there's a lot of cool stuff about that, and also about kind of the habitability of our universe and how that might be increasing as star formation overall kind of dies down. Well, not that it dies down, but the rate of star formation starts to decrease, increase metallicity overall in the universe, stuff like that. So it's a very interesting topic.
I have a question for you.
Mm-hmm.
Given that you just discussed specific telescopes and equipment that we've used to do the kind of surveys like you're talking about, what do you think an up and coming equipment that we're putting up there, space telescopes and stuff, will be the most beneficial in this continued search? Which telescope have you pinned the highest hopes on getting the most data this next time around?
I think there's a lot of really good telescopes that are up and coming, but I would definitely have to say Gaia. The third data release is coming out, I believe, in the next 6 months to a year, and it's supposed to have 10 times as many stars and better photometric analyses and stuff like that. And so, especially for my research, which is more like, I guess, star-based, I don't know, that's definitely something. But I know there's also like the SAGA or SGA survey, which is coming out, which is doing like big sky scans in the optical range, I believe. So I think that's a really cool one too. But it also kind of takes away from like the romance, I guess, of astronomy. You know, I don't know of how many, like when I go to college or grad school, how many of us will be going to like specific telescopes to get data instead of just like finding it online on big databases. So it's also, I guess, something to think about.
Have you read Emily Levesque's book, The Last Stargazers? She goes over that a little bit. It's really good.
Oh, no, I haven't. I should.
Yes, highly recommend it. The Last Stargazers.
Mm-hmm.
Camille, what was that paper that you mentioned about Earth extinctions coinciding with with arm crossings?
Let me see if I can find it. I believe it's by someone named Gilman. It was in some astrobiology journal, but let's see. Yeah, so it was Gilman, and it was 2019, and it was in the International Journal of Astrobiology. Yeah, I can send the DOI if you'd like.
Yeah, you might post it in the chat later.
Mm-hmm.
So I have a question, Camille, again about the sun's motion through the galaxy, mm-hmm. and how it, and the intersection with the spiral arm. So I've seen animations looking for, I guess, the edge-on view where you're in the plane of the galaxy, and the sun makes kind of like a sine wave going above the galactic plane and below the galactic plane. I don't know what the period is on that. But you seem to imply there's some lateral kind of motion too to intersect a spiral arm, or is it mostly just the event of passing through the galactic plane that we're talking about?
It definitely depends on the star. I mean, there is kind of the lateral motion of going above and below, but I mean, not all stars rotate at the same rate as the spiral arms. And so I think for many stars that have a lot of spiral arm intersections, that is probably a factor, not just the lateral portion, but or not just the like up and down motion, but the lateral motion of not going at the same rate as the spiral arms.
So is the spiral arm avoidance mostly because of perturbing the Kuiper belt, or is it also avoiding supernova from young stars in the spirals?
Yeah, it's both. It's avoiding gravitational perturbations that could disrupt asteroids, the Kuiper belt, or clouds, stuff like that. And then also supernovae, which could, lots of radiation from that. And I guess that's also what makes it hard to kind of differentiate between the two. If, obviously probably supernovae are bad to be around for life, no matter how advanced it is. But if asteroid impacts are actually good, it's kind of hard to differentiate between the causes of the two, which are going through the spiral arms.
So, yeah, what are the main benefits of passing through a spiral arm? If it's going to have a good upside, what is it?
Definitely if there was, it would be, which is kind of a pro and a con, but it would be the perturbations from asteroids, which could, I guess, bring life to planets that don't have life, or, I guess cause mass extinctions, which sounds bad, but I guess could be used to further the evolutionary process and help create intelligent life.
Okay. I was reading an article today comparing the habitability of F-type stars compared to G-type stars. And it discussed a lot about the exposure to ultraviolet is more extreme with the F stars, of course. But it also went on to say that it's also a good thing and a bad thing to have a little extra UV. It provides more energetic background to mix up the chemicals, but then it can also destroy DNA-like molecules. So I guess a lot of these factors can have positive effects and negative effects.
Yeah, it's very tricky, but I think if anything, that also goes to show kind of why, I guess, it's more plausible that most regions of the galaxy could have life, that we aren't necessarily something very unique or very special in our galaxy, because there are these things that may on the surface look bad, but can also have benefits. So.
Well, I was also intrigued with your statement that once life is established, it seems to be hard to extinguish it. What are the main reasons behind that?
I guess it's just all that we have to look at is our own history. We've been through like multiple mass extinctions, and each time life has come out better and I guess more intelligent. And I don't know, I guess there's just, at least on Earth, there's such a diversity of life that even if something kind of cataclysmic were to happen, there would probably be life, some type of life, maybe not our species.
So we might not have been here if we hadn't made that last crossing of a spiral arm. Huh?
Yeah.
Is there any benefit as well for the crossing the intergalactic plane? I mean, there's stuff there too, right?
I guess the benefits would kind of be the same, asteroid perturbations and stuff. But I guess the one thing that we almost for sure know is bad is crossing into the bulge, because, there's so much high intensity radiation that probably intelligent life couldn't survive. So.
Camille? Oh, sorry. Go ahead.
Oh, go ahead. Okay.
Hi, this is Courtney Rowe. Camille, what software did you use for doing your calculations, and what software did you use to graph?
I used Python for both. I would definitely recommend Python. It's definitely, I learned it online, so it's definitely not a difficult language to use, but it can create some really nice graphs. And it's also great for big data analytics. So.
Yes, I use that in GIS, so Geographic Information System. So I was as you were describing this, I was dreaming up mapping those locations as well as those possibilities.
Yeah, definitely. Python, I think, is something that could be applied to not even just like astronomy or science, but any kind of big data or kind of visualization subject.
Thank you. Great work.
Thank you.
How did you come to decide to pick this for a research topic, and what did you cast aside?
So I actually wrote a paper about the galactic habitable zone for my physics class. And I mean, I don't know, I just immediately thought of Gaia because there's a bunch of simulations and kind of trends, but nothing with actual stellar data. And so I just kind of immediately went to Gaia. For things I threw away, I don't know, there's so much kind of research out there. I was looking into kind of everything, but I definitely know I wanted to use Gaia, so it didn't feel like throwing anything away.
So is this pointing to the direction that you want your career to go in, or is this just kind of a side fascination?
I think I definitely want to do astronomy, but I don't know necessarily in like the galactic kinematics or big data range. I haven't really, I just actually started dabbling in observational astronomy this past summer, which I found really interesting. So I don't want to fully commit to like this kind of niche topic, but I think astronomy is definitely something I want to do.
I meant to ask, do you have a telescope?
I have a small one. I don't even know what it's called. I haven't used it in a while because I've been so busy, but I do have a small one, and I do have like those like binoculars, so yeah.
Okay, well, we'll have to get you to a star party one of these days when we start holding them again.
Yeah, that'd be fun.
Well, yeah, I think it's interesting in particular because we are an observational club, as you could tell, Camille, from our meeting minutes, that we do a lot of going out and looking, and we have big programs that support that. And I too have, I go out in the backyard, but I'm more in line with the kind of things you do, and I'm more fascinated with mathematical modeling and coming to take things apart through spectroscopy, figure out what they are and how they work, gaining knowledge that way. So I guess I was intrigued to discover that you have only a small telescope and you don't know what kind it is, and yet you're light years ahead of most of us in your understanding of how the galaxy and the rest of the universe work. So thanks for all of that.
Yeah, definitely. It's kind of weird that you like pointed out, but it was fun to like dabble in observational astronomy, using we used an optical telescope at the program I did, and kind of like combining the images and like learning about like flat fielding and stuff. I'd never done that stuff before, so it was really cool to do.
Okay, one of our members, Bill Schumi, is with us tonight, and he's our go-to guy for explaining how the galaxy is put together and how it hangs together. And I feel like he must be sitting on a question for you. Bill, are you still there? Do you have a question for Camille? He may have dropped off. Okay. Any other questions, guys?
Yeah, I had a question. Wanted to find out, that picture you showed of the galaxy that had that kind of a donut arrangement around it that showed the habitable region. So if you were to redraw that picture, what would it look like?
I guess it would look like a donut just with, or like a big circle around the galaxy with like a little hole cut out in the middle for the bulge.
Mm-hmm.
So it wouldn't be a donut anymore?
It'd be a very big donut. So you're getting the most bang for your buck.
Okay. Thank you.
Okay, last call for questions, going once.
I have a quick one. Okay, we're going to hope this is a quick one. I've asked this before, morbid curiosity and anything. Our first coarsest filter, I mean, you look at, okay, this is the first place we look, is the proximity to the sun, something that's orbiting the proximity to a particular star, that star being its sun. Okay, that's your coarsest filter. And after that, you have things like, okay, does this planet have an atmosphere or potentially have an atmosphere? Okay, does this planet have or potentially have a magnetic field around it, like our magnetic poles? And the question I've started asking out of curiosity, these second and third filters, which of those two in your mind would be the more important one for increasing the probability of habitability for life? The quality, grade, type, or strength of the atmosphere, or the amount of magnetic fields surrounding said planet? Which one would be more important on the list?
I guess I would say atmosphere right now, because at least for us, if we didn't have an atmosphere, besides not being able to breathe, the sun would kind of just roast us. So I feel like an atmosphere is pretty important in protecting, especially if you know like how far away it is. If it would be important in protecting life or emerging life from, I guess, the dangers of radiation, and also being able to like get out of the water onto land. You know, I don't think that would be possible necessarily without an atmosphere, but yeah.
Well, in some cases, the ability to retain an atmosphere might be dependent on having a magnetic field.
Yeah.
So your atmosphere can kind of evaporate off the top of you. So the discussions about terraforming Mars, for example, is we could build up an atmosphere, but it has no magnetic field. So the atmosphere wouldn't something to sustain it.
That's the reason I started asking this question more, because we did have someone come to another event we were at, and their speciality was magnetic fields, and we've heard people talk about atmospheres, and so I began kind of wondering and asking different people who have explored this, which one of the two, you know, just some atmospheres are going to be thicker, they're going to have different elements in them, some magnetic fields are going to be thicker or stronger, and others are not going to be as strong. And how the balance works between the two is actually becoming a pretty fascinating thing that could narrow down the filter or narrow the bandwidth of, okay, this planet may or may not be able to support life as we know it. So thank you.
Yeah, definitely. And I'm like by no means an expert in kind of the more planetary aspect, but I don't know, it's difficult to say because we only really have one thing to base it all off of.
I have a quick question. So correct me if I'm wrong, but your construct in your data is based off of, you know, just our galaxy, which, you know, is classified large bird spiral galaxy. Would this model translate to galaxies that are more elliptical or are just spiraled as opposed to barred? Or is this specific to the Milky Way?
Yeah, I definitely think since I use data from the Milky Way, I wouldn't like try to extrapolate it to other galaxies, but I think there has been work done, at least speculation work, not necessarily with data, because I don't know if we have enough like individual stars to specifically look at other galaxies. But there's definitely been speculation about different galaxies or different types of galaxies having different habitability, like having different habitability rates, I guess, or not being as hospitable to life as other types. And I think that the consensus is about that spiral arms are pretty good for habitability because there's this kind of constant rate of star formation, which helps new life, new perturbations, and stuff like that come to be.
Thank you.
Mm-hmm.
Okay, then, if there are no further questions, I guess we'll wrap up. If this were a live meeting, we would all be departing for Varsity Pizza Parlor and would buy you a pizza. But
there's no pizza in this for her, and she came anyway.
Yeah.
okay.
All right. So, Camille, we really appreciate your sharing this with us. It's a fascinating talk. And I think you're going to go far there, and good luck with your future endeavors and your future research and following your passions there.
Yeah, well, thanks for having me. I really appreciate it.
Thank you. We can try a clap again, guys.
Great job, Camille.
Thank you.
Okay, so that wraps up another meeting, guys. We'll see you next month when we'll look at the the Greek device. All right, everybody have a good evening, and we'll see you next time.
Good night.
Good night.
Bye-bye.
Thank you.
Good night, everyone.
Night all.
So Camille, if you hang around for a minute, still there?
Yep.
And we'll coordinate with Terry and get some details taken care of.
Okay, thank you.
Yeah.
Yeah, I really appreciate being invited to speak. So it was a very good experience.
Yeah, we thought I